We begin our story in the American Midwest, looking at a structure that usually symbolizes stability and community sustenance, the municipal water tower. However, the image before us represents one of the most significant public health failures in modern history. This is the story of the Flint Water Crisis. It was not merely a plumbing issue. It was, and remains, a profound public health emergency. Over the course of this hour, we will dismantle the decisions, the chemistry, and the negligence that poisoned a city. Take a close look at this image. This is not a natural cave formation. It is the interior of a water pipe that has been destroyed from the inside out. This visual degradation brings us to the core problem: corrosive water. When the city switched its water source, the new water from the Flint River proved to be highly corrosive. This aggressive water chemically attacked the infrastructure, stripping away the protective pipe scale that had built up over decades. This disaster was preventable, but it began because city officials failed to add necessary corrosion control agents during the treatment process. To understand the crisis, we must understand the element at its center, lead, known by its chemical symbol Pb. Lead is a heavy metal neurotoxin, and medical consensus is clear. There is absolutely no safe exposure level for humans. Despite its dangers, it was historically used in pipes due to its malleability and corrosion resistance, making it a common feature in older infrastructure. But when that infrastructure fails, this element becomes a silent killer. The crisis in Flint was exacerbated by the age of the city's housing stock. We must look at water pipes, the chemistry connection. Many older Flint homes, specifically those built pre-1980s, were constructed with lead service lines connecting them to the main water system. In a functioning system, properly treated water creates a protective scale barrier inside these pipes. This barrier is essential because it prevents the lead in the pipe walls from dissolving into the water flowing through them. So how do water systems usually keep us safe? It comes down to the chemistry of corrosion control. Treatment plants typically use orthophosphate compounds. When added to the water, these compounds react with the lead pipes to form an insoluble protective layer. This chemical shielding is known as a passivation process, and it is the primary defense that minimizes lead dissolving into the drinking water supply. In Flint, this protective chemistry was neglected. We witness here the failure to apply corrosion control. The chemistry of the river water itself was hostile. It contained high chloride and sulfate content. These aggressive ions actively stripped the protective scale from the pipes. Crucially, without the addition of orthophosphate to rebuild that barrier, the lead was left exposed and leached directly into the water supply. Let's break this down to the molecular level, looking at dissolution and solubility 22. As the water chemistry changed, lead dissolution increased dramatically in the corrosive Flint River water 23. We can define this through a specific oxidation reaction 24. Solid lead, represented as PbS, transforms into dissolved lead ions, Pb2+, Aq, releasing 2 electrons in the process, 25. This creates the toxic solution that flowed into residents' taps. Lead was not the only chemical concern. We must also examine the role of chlorine in the crisis. As the river water was difficult to treat, massive amounts of chlorine were added for disinfection. This excess chlorine reacted with organic matter to create byproducts called trihalomethanes, or THMs. These THMs are regulated carcinogens, and their presence served as an early warning sign of total treatment failure, long before the lead issue was publicly acknowledged. The failure of chemistry led directly to a failure of public health. The health impact was wide-ranging lead poisoning. The consequences were most severe for the most vulnerable. In children, exposure caused reduced IQ, learning disabilities, behavioral problems, and anemia. However, adults were not immune. They suffered from high blood pressure, kidney damage, and reproductive problems. The damage done to these bodies is often irreversible. How did this go on for so long? The answer lies in the methodology of testing the water. Investigations revealed that city and state officials used misleading pre-flushing methods when gathering samples. By running taps before sampling, they artificially lowered the lead readings. It took independent researchers, specifically teams led by Dr. Mark Edwards, to expose the true, dangerous contamination levels to the world. This crisis was not an accident of nature. It was a failure of governance. We must scrutinize the role of government and transparency. The tragedy occurred because multiple government levels failed to prioritize public health over financial austerity. For months, officials dismissed evidence and complaints from residents, systematically eroding public trust in the very institutions designed to protect them. We cannot discuss Flint without discussing environmental justice. The demographics of the affected area are stark. It is a predominantly low-income African-American community that was disproportionately harmed. This raises uncomfortable questions about equity. The evidence suggests that cost-cutting decisions unfairly targeted a vulnerable population. A classic example of environmental racism where marginalized communities bear the brunt of hazardous pollution. To fully grasp the science of this disaster, let's review the water chemistry vocabulary. We've seen corrosion, which is the chemical wearing away of materials. We've witnessed leaching, the process of a substance dissolving from a solid material into a liquid. We discussed passivation, the method of forming a protective non-reactive coating inside pipes. And finally, solubility, the ability of a substance to dissolve in water, which was the mechanism that mobilized the lead. Once the truth was undeniable, officials had to enact restoring the water, short-term solutions. The first step was an immediate switch back to the Lake Huron water source to stop the corrosive input. Simultaneously, they began aggressive orthophosphate addition to coat the pipes again, and NSF-certified water filters were distributed to residents to provide a temporary safety net. Filters and phosphates were only stopgaps. The city needed restoring the water, long-term solutions. This led to the initiation of the Lead Service Line Replacement (LSLR) program. This is a massive infrastructure project with the goal of physically digging up and replacing lead pipes with safer copper or plastic pipes, ensuring the hazard is removed from the ground entirely. The crisis moved from the laboratory to the courtroom. We are now seeing the legal and ethical aftermath. In the wake of the disaster, numerous lawsuits were filed against state and city officials for negligence. Beyond civil suits, criminal charges were brought against key decision makers, sparking a nationwide ethical debate on public servant responsibilities and accountability. Flint served as a wake-up call for the entire nation regarding lessons learned infrastructure. It highlighted the urgent need to upgrade aging water infrastructure across the U.S., much of which relies on outdated materials. It also proved that regular, non-biased testing and full transparency are essential to prevent future public health catastrophes. The crisis also redefined the relationship between lessons learned, science, and policy. It demonstrated that qualified scientists are essential in municipal decision-making. Engineers, not just financial managers, must be heard. Ultimately, we learned that policy must be driven by scientific data, not cost-cutting, and there must be stronger lead and copper rule enforcement at the federal level. The tragedy is highlighted by the difference between the two water sources. On one hand, we had comparing water sources. The original source, Lake Huron, was characterized by low corrosivity and stable pH, which required only basic treatment. In stark contrast, the Flint River was known for high corrosivity, high chloride and sulfate levels, and highly variable quality that challenged the treatment plant's capabilities. As we conclude, we leave you with a call to action. Your role. Do not take your tap water for granted. You must understand your community's drinking water source and learn to read quality reports. Be vigilant and advocate for infrastructure improvements and environmental justice in your area, so that a tragedy like Flint never happens again.